say first, and then I introduce the book. You join, John?
Yeah, join.
Feel free to take a.
Okay, yeah, we have critical mass to start. Welcome, everyone. This is the first AI in Health seminar of the semester. We're really excited to have you either online or in person. We have a bunch of really good speakers, some external, some internal, and the cadence is going to be every 2 weeks. The talks will be 30 minutes on Zoom, but afterwards we have an in-person component on Del Med campus. And really the goal of the in-person part is to put together computer scientists, engineers, AI researchers with clinicians and try to come up as a group with actionable projects to try to tackle. So we were a little bit late in sending this in-person invite, but it'll be happening again in 2 weeks, either in this room or a room adjacent. So look out for those emails and really come with ideas that you think are actionable and would have some impact. And you're either looking for clinicians or you're looking for scientists to help do it. So that's the goal of this. The lunch will be provided up to room capacity every 2 weeks. So I'll let Ying introduce the speaker, but thanks everyone who came in person and those online. We hope to see you in person next time.
Thank you, John. So I want to introduce our first speaker. So Dr. Carl Yang. So Dr. Carl Yang is an assistant professor of computer science at Emory University. He jointly appointed also Department of Biostatistics and Bioinformatics in the School of Public Health. So he actually he did his PhD at UIUC in computer science and spent a lot of time on graph data mining, applied machine learning, knowledge graph, and federated learning. Since he moved to Emory, he spent a lot of time in healthcare. So basically, his research is published already in a very productive 150 peer-reviewed papers in top venues, and is also received a dissertation award from UIUC and Best Paper Award ICDM in 2020 and KDD Health Day in 2022, and also Best Paper Award for Machine Learning for Health Conference in 2022. Wow, there's so many awards. I will skip those awards. Okay, so let's, his also research is funded by both NSF and NIH. Yeah, let's welcome him to give his talk.
Yeah, thank you, Dr. Lin, and thank you for having me, and thank you for the very nice introduction. These are small words, but yeah, hopefully it's gonna help the research and also help promote some of the findings. So yeah, I'm very happy to be here and briefly talk about our current research and more like a vision and agenda on this knowledge graph and language model co-learning thing, right, for healthcare. So here is kind of an overview of the things we kind of lined up maybe 1 or 2 years ago, and now it's currently moving still very much under this picture. So on the one side, you see knowledge graphs, right? This is something I have been working on for many years, and now it just become more interesting as we look at its potential interactions with language models, right? So why we use, I have a few slides on further discussing why we need the knowledge graph, what maybe knowledge graph can do for healthcare, right? But in general, we know there are accurate knowledge in knowledge graph, and this knowledge can also enable some explicit reasoning on it, right? And it's also relatively easy to edit the knowledge, right? Compared with language model, right? But the knowledge also need a lot of standardization, and we know the major limitation is the knowledge is often incomplete, right? The coverage is never as good as nowadays very large language models, right? And there is also gap to application. So you need to somehow formulate learn embeddings or formulate the problems as a reasoning problem on the knowledge graph to really answer certain questions, right? On the other hand, I don't need to further emphasize why large language model might be a powerful tool, right, for a lot of applications, including healthcare. But in the same time, we know there are limitations of doing things with lack of planning and doing fuzzy inference and has a lot of hallucination problems that really make it pretty challenging to apply it in everyday health clinical workflows, right? So the research we do here is we try to leverage both of them and in both directions. So we try to use language model or more commonly or more broadly multi-modality large foundation models, right? To help us automatically construct the knowledge graphs, and really to mine new knowledge from different sources of healthcare data, right? And then we're also in the other way, after we get more better knowledge graph, or even with the existing knowledge graph, we have been studying techniques of using the knowledge to guide planning, to do reasoning, or to do a post hoc checking of the answers generated by language models. So these are two-way interactions. In the same time, we are kind of envisioning this federated system, multi-agent system, but powered by federated collaboration. So the idea is we want first we want to have a more language-based interface for models to collaborate. So the opportunities here would be this language-based collaboration might be a better way of collaborating the models nowadays, because previous a gradient share or model share, this kind of communication probably are not so guaranteed towards the protection of data privacy, right? But through language, we are building certain certain methods to make sure we can have closer check or closer track of the communications of the model collaborations, especially across institutions. And we also think there are a lot of opportunities for health providers or different stakeholders in the healthcare community, right, to contribute to this multi-agent system. And also hopefully this eventually will be able to help us remove bias to address disparity, this kind of very important societal problems. So this is the whole picture, and I'll go into more of the details. But the first question is, right, why do we really use knowledge graphs for healthcare? So, so modeling the risk factors or medical concepts, right, have been have been a task for a long time. But traditional in health informatics or in epidemiology, people often model these risk factors isolated. And also, even for modeling them together, it's often just a few of them, and not really modeling their explicitly model their interactions. Right? So, graph is a way to model to really look at the potential interactions among different risk factors. Right? And graphs provide this structure, so we can do implicit reasoning, such as by finding certain subgraphs or certain paths on the graph, right, to enable us to generate more complicated reasoning. So and finally, the thing is that knowledge graph is still a pretty flexible thing, as we will show. We really look at knowledge graphs a little bit beyond what people look at knowledge graph nowadays, right? To try to make it available, to make it possible to accommodate different types of healthcare data. So this first type of graphs we have been working on, I have been working on during most of my PhD years, is this so-called heterogeneous graph. And there's basically a heterogeneity of entities and relations in the graph. So these entities in our scenario could be diseases, could be gene factors, right, drugs, and procedures, right? So a lot of different kinds of things, but each of them could have different semantic context. You might use different language or even use imaging to give to use as features of these nodes, right? And then you can use different kind of encoders to project them into the same space and then try to find certain certain patterns, right? So in earlier years, I have a lot of work basically directly on this kind of heterogeneous graphs. And then another thing we look at is the hierarchy in the knowledge graphs, especially in the healthcare scenario. So for example, in the middle, we can see a hierarchy of diseases, right? So when we work with clinicians and try to say we extract some diseases from like a EHR report or from like clinical notes, right? Can we really put this like can we really know which diseases this new entities correspond to in an existing knowledge graph, right? So we can extract, so we can also get the like relations and the other relevant entities, right? But to solve this task, we find that when we ask clinicians if two diseases with different names are the same thing or not, it's very hard for them to tell you if the two things are equivalent or not. But instead, what they usually find to be easier to do is tell you the disease A belongs to disease B, or disease B like belongs to disease A in the other way, right? So this basically says there is naturally a very common notion of ontology or hierarchy in the healthcare, in a lot of healthcare knowledge graphs, right? So that basically means when we try to, let's say, compute embeddings or do like a mathematical computations over these entities, we need to respect or leverage this underlying hierarchical structure. So we have in the early years when since I joined Emory, I have been working on a few like geometric embedding methods, right, which is shown to be more powerful to accommodate the hierarchical structures to make more efficient usage of the embedding space and be able to really differentiate the entities that are just children of the same entity or like basically exactly the same entity, right? So this kind of work like a knowledge graph, this is kind of a knowledge, this kind of a special like a property of knowledge graph we look at when we look at knowledge graphs for healthcare applications. One of the last things I also want to highlight is this notion of hypergraph, or like nowadays we call it a contextualization of the knowledge. So what we believe here is there's a lot of knowledge in the knowledge graph, and there is this kind of, people are trying to build this kind of global knowledge graph, which tries to encode this accurate knowledge, right? But in reality, the knowledge hardly like generalized. There is hardly like knowledge that really generalize across all of the different situations. So a more like appropriate way to understand the knowledge could be a certain drug treats a certain disease, right? But this only happens for a certain type of patients, right? If the patient has some kind of comorbidities or has some kind of phenotypes, right? So you will use this drug, right? It's unlike you will use a certain drug to treat this particular disease for everyone, right? Like considering the heterogeneity of patients, considering the complication of the diseases, right? So this way, so this is a way like we try to use this hyper edge or this kind of higher order context, right, to try to find or like associate an appropriate context to the knowledge graph, right, to each part of the like subgraph. So we have been doing this like a knowledge graph and hypergraph co-learning kind of thing on the based on EHR data and external knowledge graph, and that best paper award we had in the ML4H conference was basically a more like a causal inference pipeline, which allows us to find subgraphs within like a larger within a patient visit, right? And this is basically this subgraph basically corresponds to a specific condition of the patients, right? So this gives context to how we model the particular, even the same like entities, how we can model them differently for each patient. So these are those were some of the like kind of spatial graphs we are trying to basically look at, right? When we really put knowledge graph in the context of healthcare. And here are a few applications we've been working on. The first one is more like a brain network, like a brain imaging setting. So this graph is not a traditional knowledge graph. It's more like the kind of brain connectome. It still encodes like entities of brain regions and their relations, but not like a general knowledge graph, right? But we still understand it as a knowledge graph because it provides relations about entities, and these are more like some kind of external knowledge that could be used to conduct certain analysis. Multimodality biomedical AI is another thing we've been working on, especially recently. And there are different scenarios. We started with the EHR data, and we try to put in like omics, like behavioral data and the mobility data to make this really like more comprehensive modeling for the patients. Right? So we've been doing like building basically different kinds of prediction and analysis model on risks, on subtypes of complicated diseases, and also on treatment and the progression of the disease. So almost all kinds of like prediction tasks that you can think of doing by using machine learning models. So now I want to go a little bit further into some of the each of the thrusts, right? Like the major like kind of direction we are working on. So the first one is again from language model to knowledge graph, right? How can we use language model to help the construction of knowledge graphs? So in the middle is actually the first kind of work we are doing. So the basic idea is the knowledge could be from different sources, different institutions, different universities and labs, right? And they just commonly use slightly different. They just hardly use the same like terminology all the time, right? So they will even some of the open like knowledge graphs. They pick different kinds of naming systems or coding systems, right? So the first thing is you have so many existing knowledge graphs. How can you put them together, right? So there we started some, like previously we started some graph alignment based method, but now today I want to talk about a very like kind of a very neat one using just language model, doing prompt engineering using language model to help this alignment, right? And then I won't be talking about details about either side, but the left side is more about how you can verify the knowledge, just to guarantee the quality of the knowledge in a knowledge graph by doing RAG on the relevant documents, right? And then on the other side is like a multimodality knowledge extraction. So we also leverage like a large vision model, large like a time series foundation model, try to extract like a multimodality biomarkers and also associate these biomarkers, these multimodality things into the knowledge graph, right? And we do this by really like extracting new knowledge from patient data, real patient data, real like multimodality data collected in our like Emory hospitals. So this alignment work, I just want to talk a little bit about. It's done like 2 years ago. So at that time, like even like prompt engineering was just a lot of people doing that, but just at a very beginning kind of time, and also RAG was not really a thing. Like a retrieval augmented generation was not really a thing, but you'll see like in this work, actually, both things are explored pretty nicely. So the scenario is, right, we have multiple knowledge graphs. And the special thing is in the middle, we always want to align these knowledge graphs to a ontology. So like we said, right, we find the ontology to be a very like important architecture, and people have been really working hard to standardize these things in knowledge graphs, right? So now when we have a new knowledge graph or we have new entities, we always try to align it to a ontology first, right? If we can align it, nowadays we have work to study how we, let's say, expand it or how we insert a new node into the ontology. But this work assumes we can align everything to existing ontology. So, right, this is more like the mathematical, like a kind of formulation, right? You have a knowledge graph, and in the same time you have ontology, and you just want to align those nodes that doesn't have the exact same name. Any node in the ontology that has the exact same name, right, doesn't have the node there. So we want to align this node, try to find the closest node, right, you can align to. And then we build this kind of a retriever plus re-ranker kind of framework. At that time, we didn't know RAG, right? But this happened to be a very kind of a similar thing that people are doing like intensively nowadays. So at that time, the major observation was if we want to, let's say, given a new like entity in the knowledge graph, right? If we want to align it to a existing ontology, right? We need to put the whole ontology into like, if we want to have a large language model to help us do that, we need to put the whole like ontology to the input of the language model, which is just not doable, right? So very naturally, then we need to do a retriever step first, right? To use some more traditional method to find like a substructure or a certain part of that ontology, right? As candidates, and then put those like smaller ones into the language model, right? And then ask the language model to re-rank these things. So this is like the overall framework. But something we find to be useful is, of course, on the knowledge graph side, right? This entity we are trying to align to the ontology has some neighbors, has some relationships with other relevant entities, right? So we want to also make use of this. So another thing is on the ontology side, right? We know there are like relations or structures on the potential entities you are aligning to, right? So this knowledge we also want to leverage, right? But eventually, the way we find to leverage both is the optimal way turns out to be if we use this knowledge graph structure, right, on the retriever side. Basically, this gives more like information to the retriever, so it knows how to. So it can basically compute better embeddings to basically retrieve the more relevant entities from the ontology. And then the ontology side, we find that this knowledge about the ontology actually helps large language model to make better choices. So we have some like case studies basically showing, for example, there is a syndrome, and there is some particular syndrome. If we want to align, we want the language model to find like the appropriate like syndrome to align to, it will always tell you some like restrict it to some other syndrome. But the syndrome we are looking for is probably just not a particular syndrome. It could be a disease or something. So if the language model doesn't have knowledge about the ontology, meaning that some syndromes can also be diseases, right? If it doesn't have this knowledge, it just will never give you that disease name, right? So this basically says like if we put the ontology structure in a way that language model can understand, right? At that time, it's just by this kind of context, right? You just basically write about each relation and semantically describe each relation and put them into language model. And then they will be able to generate a much better like outcome. So in order to evaluate it at that time, I also needed to create two new datasets, right? Where you have knowledge graph and ontology both in the dataset, and some of them are actually describing the same things with different names. So that was not a very like a common. That's a commonly seen scenario, but in order to find that dataset, still we needed to like to search through some of the resources. And then we evaluated this like the so-called high prompt method, right, with respect to like existing retrieval-based method and some language-based method, and also like embedding-based method, right? So we got like much better performance in both of the zero shot and one shot scenario. And then we also checked whether we added these attributes structures into the retriever, into the ranker actually helps, right? And also like at that time, we tested it with different language models, and some of the language models perform better, basically the more powerful ones, right? Eventually achieved better performance. But for the simpler ones, what we observed was this high prompt structure actually is able to improve them more significantly, right? Just compare, let's say, this row the second row here, right, with this second row here, right, you can see a much better, like a much more significant improvement for the happening on the smaller model, right? So this makes sense because your larger model might have better understanding of the structure anyway, right? So the method we use doesn't help much, but being able to help the smaller models in healthcare usually is also a very important thing. So some of the case studies, including this kind of syndrome kind of scenario, right, showing like why knowing syndromes could be disease is helpful for basically aligning this particular syndrome to another like existing syndrome in the ontology, right? So I think I'm kind of running out of the time, so I will try to like skip some of the content, but let me talk about this particular slide because it's more of a summary on what we are trying to do on the like other side from KG to like language model, right? So this basically shows like one of the examples kind of preliminary studies we did. So we try to use language model to do risk prediction. And what we observed there basically is it can do like it cannot really outperform like traditional machine learning models, right? And then what we really observed, one of the reason we found is the language model can hardly, so given a particular risk prediction like a target, right, a particular risk to predict, language model doesn't know what kind of other risk factors or medical concepts could really like contribute to this prediction. So in other words, like your traditional like methods through training, it can quickly identify the important features, right? But your language model cannot do that. And there is one thing we find to be useful is we can directly tell the language model. If we can tell the language model what factors to look at, it will perform much better. So those results were shown in one of the paper, this EHR agent paper, right? So basically, if we ask the language model a question and in the same time also tell it what information to retrieve, then it can answer the question pretty well. So this, motivated by this, the first thing we are trying to do using knowledge graph to enhance language model is to provide this kind of context, right? When you ask a question, we extract entities from the question and then try to find the relevant entities in the knowledge graph and then use these relevant entities as a guidance for the language model to do the RAG, right? So this is something that could really help like a lot of predictions. And another thing is just to do like more like a rule-based reasoning, right? We have an algorithm compared with like a kind of a state-of-the-art algorithm called chat rule. Our algorithm can more efficiently find like neural symbolic rules, and then we use like fine-tuning to tune these rules into the like language model to make them able to make this kind of rule-based reasoning, right? So there are several works ongoing as well, showing like how we can do to really improve them. To on the one side to make language to let language model help us find more rules, right? And then in the other way, use these rules to fine-tune the language model to do the like rule-based reasoning. And finally, there is like you can always do like planning reasoning, right, to try to improve the like performance of the language model, but you can't guarantee the outcome is error-free. So what we are also doing is like a post hoc kind of a check or a post hoc reflection scenario where we like have the answer, we get the answer, but then try to reversely decompose the answer into atomic claims and then try to check each of the claims on the knowledge graph. And one limitation is this has a good accuracy if you can find the like evidence from the knowledge graph. But again, the knowledge graph itself is incomplete. So a lot of things you can just hardly check. So when you don't have the evidence to support, it doesn't mean it's wrong, right? But it really doesn't tell you much about whether it's wrong or not. It just tells you you cannot check it. So in this thing, for this scenario, this is just another motivation for us to keep improving the coverage and the quality of the knowledge graph. So I will have to skip this work, but this work is more about how we combine kind of the language model with a hypergraph model we developed before, right? To really do like to allow the model to model both the semantics of the entities, the medical concepts, right? And also model the interactions among these concepts. So I'll need to go like really skip the results. And nowadays, we are also using knowledge graph to try to do derive more like a validation benchmark data set to really exactly evaluate the kind of hallucination and the misinformation kind of risks or the issues of language models, especially in the healthcare domain. This is kind of the federated learning scenario we are envisioning, right? Through like a model collaboration, through communication, language-based communication, and how this might be useful for us to engage human, especially. Here, this is just a very brief discussion about our guard agent, our recent guard agent work, where we basically build a LLM-based agent to check whether the communications include privacy information. So this will become, this guard agent to our like federated multi-agent system is just like a differential privacy to any existing federated learning system. It adds another layer of privacy towards like the data, adds another layer of protection towards like data privacy. We also want to involve like health professionals, different health professionals, and also consider the kind of the SDOH factors, right, to really try to address some of the more societal problems. But this is like very much like ongoing visionary work. We haven't really been able to do much on this yet. So with that, I kind of rushed through some of the slides. I'm really sorry about that, but feel free to reach out. I think any kind of collaborations with health professionals, with people interested in AI, in large language model, we have a lot potential to collaborate and to discuss. Thank you.
Okay, thank you very much, Kyle. Great. We have maybe a couple of minutes for questions. First to check whether we have some people online has questions. If we have people here has questions, then I will repeat the question here. So any questions? Yeah, Alex.
For a great, like, is there a similarity with like principal component analysis? One method, other advantages, method, and other, like for this than for like a principal component.
Okay, great. Kyle, the question is, people in clinical domain, they get used to, they're familiar with principal component, PCA, principal component analysis. And you talk a lot about the deep learning and all the embedding and all the generated model. So how this embedding actually, we can use PCA to work on the embedding, or the embedding is PCA, how this related? Yes.
Right. Yeah, I think that's a very, very interesting question, right? So PCA basically finds like I guess the question is about when we model the interactions among some variables, right? Is that something similar to what we can do with PCA? I assume, or maybe the relation between knowledge graph and PCA, right? Is there some kind of relation similar to what has been modeled by PCA, right? So I would say that's really an interesting question. Like for knowledge graph, I think the relation is really like rich, and really like you can basically consider whatever kind of relations, right? But PCA, I think, is more about like orthogonal, important like features that give you more variance about the data, right? So I would say like in this sense, like the type of relations PCAs are looking for is just a very tiny subset of what we can possibly model with knowledge graphs. Another thing is maybe I didn't understand the question perfectly, but I think the question is also about if we compute embeddings, let's say from knowledge graph or from language models, can we do some kind of PCA analysis on it? right? Of course, I think doing that would be helpful. That could help us to do computations, right? At least reduce the embedding size or whatever, right? But one caveat is these embeddings themselves, they are more of a an implicit thing or in the some kind of a latent space, right? So that means it really already lose the interpretation. Right, so I think one very strong thing for PCA is it tries to really be able to capture the important dimensions and then explain it, right? But for embeddings, you don't you really don't have this kind of interpretability. You need to work with some more symbolic things some methods to basically project these embeddings back to the knowledge graph to try to get interpretation.
Okay, great. I think I didn't have any question from online. Do we have one more questions? Otherwise, we're good. Thank you very much, Kyle. Thank you.
There is one. One.
Oh, there's
online.
one? Where? I don't see any.
It was there just now, but now it's put down.
Disappeared from the
Hi,
chat window.
I just had a quick question for you.
Okay,
The
great.
fascinating work. I noticed, I was surprised that your instruction tuning performance is kind of low. And I wanted to ask if you had some insights or if you tried fine tuning on the language model to see if it could reason it better.
Right. Yeah, that's a very good question. So, right, about that, I know you are talking about this one, right? So, yeah, that's a very nice one. So, yeah, we did instruction tuning and in context learning. I think both gave improvement, but the thing is, language model is not really made for making predictions. So their power, I think, is more on reasoning about things and at least generate some kind of things that looks like reasoning, right? So generating more semantic rich outcome, like generating reports, generating notes, kind of things, right? Or generating even conversations. I think these are strong. But for instruction tuning, I think that for making predictions, even with instruction tuning, it's really pretty hard to achieve better performance. And another thing is EHR data, the input we give language model in this project is really complicated, and it's basically a combination of numeric things, right? Categorical things, right? And they are many of them are just irrelevant. But when language model tries to look at these things, they try to find correlations or try to find relations between these things to the prediction, and they tend to be more kind of conservative on certain things, right? If they find something that is really not so relevant, but they try to be cautious, they try to give you a more conservative answer, then it's very hard even through instruction tuning to make it become more aggressive.
Great. I think thank you. And time-wise, we finished talk today. Thank you, Kyle. And the video will be posted on the website. Thank you.
Thank you, Dr. Ding. Thank you, everyone.
Bye.
Enjoy the lunch and discussion. Yeah. Hope I could be there.
Mm-hmm.
All right.